All right, welcome. So sorry for not being in person for the last couple of classes. Hopefully won't have that happen again. I'm a little bit ill still. Tomorrow I do have to take a family member to a doctor's appointment. So my office hours normally in the morning, I won't be available, but I did make an announcement that I will be here tomorrow from 4 to 6 in my office to make up for the basically I'm not canceling it, rescheduling it. So if that causes any conflict, just let me know. We can try to work around it as best as we can. I did put on content. So I only did this not to be sneaky, but just to make it so that it doesn't cause any agita. I put it here. So on a 328, I put the exam 2 review. That should be available to you. So I didn't put that here for today's class, only because I just didn't want to conflate things to go from there. I just realized too, I thought I had put this up, but I did not. So let me just go ahead and upload the presentation today. So that's going to be system errors. Wait a second. Yeah, okay, steady state errors. Just do this file real quick. And we should have that. Okay, should be available. All right, so any questions before we jump into new material? Because everything on the test, this is new material. So anything from today forward, unless you have questions, obviously, is going to be new content, new material. So any questions on anything? I know we've had a boatload of homework. I've been trying to post the solutions. Those are all available for the homework that is already due, correct? Does anybody have any issues with that? Everybody hopefully knows where to find them at this point. So in the content folder, I think that's under homework solutions. I believe that's where that all is. The grading for the lab is a little bit slow, but hopefully we'll pick up, get that going pretty quickly here. So let's talk about steady state errors. Let me get this out of the way and that. Okay, so I've said this, I don't know how many times in this class, but we live in the time domain, but analyzing systems in the time domain can be quite difficult because we have to solve differential equations. So what we'd like to do is to figure out time domain response or time domain expectations, time domain characteristics, whatever you want to use for a phrase, to go ahead and get those results, but to not necessarily work in the time domain. And one of the big things we have is our steady state response. What is our final value going to be? And a couple examples I came up with is, what if you're coming up with a set point? And a set point is what you desire, what you want to achieve. So if I want the temperature in this room to be 70 degrees, then I set the thermostat to 70 degrees. And there's a loop, a closed loop, that actually will tell me, is my temperature in the room approximately 70 degrees? So everybody understand the concept of deadband? You could never really get to perfect 70-degree room temperature because it's going to get to 70. And then if it shuts off, then it's going to cool down and it's going to kick back on. So you'd be constantly chattering on, off, on, off, on, off. That's not practical. So the concept of deadband is not, let's say I want it to be 70 degrees. So if it's 70 degrees in the room, the heat for this room could be on or off. We don't know that. So the concept of deadband is I have to know what's happening before that instant in time, if it's within the deadband zone. So 70 degrees is an ideal temperature, or the temperature I want, but the heat may be on or off. It just depends. If the room was below, let's say my deadband is 2 degrees. If the room was below 69 degrees, then the heat kicks on. and it raises the temperature in this room until it gets to the end of the deadband, which is 71 degrees. Once it gets to 71 degrees, it kicks the heat off. So it goes back down. The temperature starts to drop again until it gets to 69. Then it kicks on and goes off. So the deadband concept is the heat could be on or off between 69 and 71 degrees. You don't know. It's dependent upon the previous state. So a deadband means I could be in either case. I don't know where the term dead comes from. I guess you could be alive or dead, maybe depending on your perspective of things. But the idea is that the concept of deadband, that's a control characteristic, because there are very few systems that have to be maintained at such a very tight tolerance that they can't tolerate some change, especially if it's something that can't be held at a constant. Temperature is one. How about chemical properties is another one. Alkalinity, for example, especially if it's something that is going to change based on, like, we lose heat in this room all the time, or heat is added to this room all the time. So it's harder to control temperature. That's why you have that set up. But that is a closed loop process, because our thermostat has a dial to indicate the temperature we desire, but we also have the ability to monitor, I mean, measure the temperature, and then it looks at the difference between those two. So we're not going to focus on this deadband concept. We're going to focus on achieving our ideal steady state value. Maybe it's a speed or a distance or a level. Any one of those. Excuse me. This is my second class in a row, so my voice is starting to fray a little bit. So those are constant levels. Level in a tank. One of the big things is level control in a tank, because we want to maintain that level at, let's say, 60% of nominal, 60% full. So that would be a case where we'd want to monitor as well as have a set point value for that. But that's not necessarily the only case where we have a fixed value. Some of the harder ones are tracking. Let's say that I want a car to be moving at a certain distance away at a fixed speed. So I can either set the speed, or the distance away will be increasing. So if I have a robot, I want it to be 1 foot away, then a second later, 2 feet away, 3 feet away, 4 feet, on and on and on. That would be a ramp characteristic. So I'm ramping my set point input, and my control is making the robot go ahead and increase the distance that way. So maybe I can't monitor speed for some reason, but I can monitor distance. And so at that point, I'd be ramping it up. Parabolic would be another one. Maybe I'm trying to accelerate something. So I want to continue to accelerate it. So at that point, I need to increase it parabolically. That's a less common one, but the idea is that our inputs may not necessarily be a unit step, a unit ramp, or unit parabolic. I would like to have a controller design, or I want to go ahead and assess what the capability is, my system, by calculating the error for these different type of inputs: step, ramp, parabolic. So here's our system. And we talk about having unity feedback. It doesn't have to be unity feedback. We can have an H value in here. It's just sometimes easier to talk about unity feedback. Unity feedback means I'm directly comparing my output to my input. So intuitively, it kind of makes sense. If I want 72 degrees or 70 degrees, and my output is 70 degrees, I want to compare those two directly. So going into a summing junction, it makes a little more sense that the input and the output are the same, parameter that I'm trying to control, so that I can get error here. And what I'm trying to do is calculate the error and force that error to be 0, because I have two controllers or two systems here. I have the plant and I have the controller. The plant is just the physical system. So in this room is our plant. This has a first order process. We put heat into the room, or heat is extracted from this room. The temperature is going to go up or down. That's basically a first order process. Our controller is the thermostat. It's either having an output to turn the heating system on or to turn the heating system off. Binary, right? 1 or 0 for the thermostat control, because unless you have a more elegant heating system, at least in my house, the furnace is on and it's pumping water through the radiators. or the furnace is off and it's not pumping. All right. So this controller is, you get to add this. You add the controller into your system so that you can force your output to be what you want it to be for your set point. Your controller here can be a proportional integral, proportional integral derivative. That's why you might have heard the term PID controller, has proportional, integral, and derivative control built into it. Most controllers today have all capabilities PID, and I haven't done a lot of process control, so I can't talk about it with a lot of expertise, but all the stuff I've ever seen is you hardly ever implement derivative control. You do proportional plus integral, because integral is integrating the error. Remember, the signal coming into this controller is error. So I can either have an output that is proportional to the error, that is the proportional plus the integral of the error, or the proportional, integral, and derivative of the error. So most of the time, if I just have proportional, so if it's P only, excuse me, then I always have to have error, because if you think about it, the only way that my controller is going to have an output here with a proportional control is P times the error. So proportional only controls work on the concept of you always have to have an error signal. Which, is that what you want? If you're trying to control something, you're trying to set a set point. I want it to control the 70 degrees, but the temperature's got to be at 68 degrees to get to 70 degrees, right? It's always going to have a forced amount of error. So what do you do at that point? You start cheating, which is, I really want the temperature to be 70 degrees, but I only will get 68 degrees if I set it at 70. So what do? You turn it to 72 or 73 or 74. So you start kind of cheating your system a little bit to go ahead and get what your desired characteristics are. And so that's where you get some, some plant familiarity. If you get some, you're just the expert at your systems and you know how they function. So you tweak things. Normally this is the value that I want, but I got to dial it back or I got to dial it up. So that's just becoming more familiar with the system. So that works, but it is a dangerous precedent, because as we move more and more to digital control, the computers don't necessarily have that capability of remembering, hey, you need to set it 2 degrees above. That's what the operator would do. So you're better off to go ahead and design a system that can reduce that error to 0. So by adding an integral, right? Remember, if this is my error signal, let's say it's a constant, the integrator here is going to do this. It's going to increase until the error drops back down to 0, and then it stays flat. So an integrator is basically a memory feature. It remembers I need to go ahead and keep that value output. So an integrator will remember that feature and will keep its output after the error has gone away. So you don't need any error with a proportional plus integral control because of that memory feature. The addition of derivative, the only time I've seen it a derivative is sometimes proportional and integral is a little too fast. So like on a temperature system where if you're trying to maintain tolerances of a temperature, if you have proportional and integral, you set the gains of those independently, and sometimes they can overshoot, because if you're increasing your temperature and you're continuing to integrate your error, you can overshoot quite easily. So you use derivative to actually slow down the performance of your system. So most of the time, what I've seen is proportional plus integral minus the derivative to prevent so much of an overshoot. Okay, but again, I'll be the first person to admit I don't have a ton of process control experience where I'm doing it. But for all the stuff I've seen, when I did do a little more process control, if you did do derivative, it was minus the derivative, and it was usually only in temperature control. So like if you were doing semiconductor manufacturing and you were trying to control things with temperature, you would actually put a derivative in there minus the derivative. Okay, so let's get back to our steady state error. So I'm trying to calculate the error here, the difference in between the set point and or input and the fed back value. So ultimately what my error is going to be equal to my input minus my output, right? So another way of saying that is if I open this up, so if I break that open and just look at that value there, that plus to minus, and do the gain of that only, that's going to be more effective to me. So I will open the loop. We talked about a closed loop gain where we go ahead and write the G of S, which is, or the closed loop gain, which is a C over the R. This is the open loop gain where I'm looking for the error over the R. So I open the loop for that. I don't do G over 1 plus G. My open loop gain is simply here. Okay. So my steady state error is going to be equal to, using my final value theorem, this right here. Remember the properties from our Laplace table? Let's check and see. Let's see if we can bring that up. Final value theorem. I want the final value. So I want to know what the final value of my error is. That's my steady state error. So the final value is a limit as that error function in the time domain as time approaches infinity is, let's see if I can find it here. Let's see, I guess we'll have to go here. That's way more detailed than I want it to be. I just want it to be a simple one. Here we go, right here. So the final value, f of infinity, right, is equal to the limit as s approaches 0 times s times f of s. So whatever this function is in the Laplace domain, so take my error function, my e of t, convert that into the Laplace domain, that becomes e of s, multiply that by s, and take my limit as s approaches 0, and that's my final value. Okay, so I'm going to use the final value theorem to go ahead and get there. So here's my, whoops, why isn't this? It's a little slow today. So I'm going to use my final value theorem, which is R of S minus C of S. My C of S is equal to here. Do you need me to do the math, or do you feel pretty comfortable how I got this over here? Everybody see how I got this? Let's just do it because sometimes the math gets a little bit confusing. So this right over here is the closed loop transfer function. This C of S times R of S is equal to G over 1 plus GH. Remember that we did that with block diagrams. We did that 1,000 times. So C is equal to R times G over 1 plus GH, correct? So the G here is GC times GP, and the H is equal to 1. Okay. So in this formula, my G is here. My H is equal to 1. So that's basically the G over 1 plus GH here. And then I multiply my R value here. Now my error, my E of S is R of S minus my C of S. So I'm going to write that out. So that's G, C, GP over 1 plus GC, GP times R of S. Now I put that under a common denominator. So 1 over GC, GP. And then this is going to be equal to R of S times 1 plus GC, GP minus GCGP times R of S. And then you can see that these two terms will cancel, right? Everybody see how those cancel? And so I'm left with R of S over 1 plus GC times GP. Okay? That's where this expression came from, is just putting it in a common denominator and doing all the math. So to solve for the steady state output as a time approaches infinity or a final value, I'm going to take the limit as S approaches 0 of S times E of S. That's what this expression is here. I don't want to go to the time domain because I'm going to do all that partial fraction expansion stuff, right? That's no fun. So why don't I go ahead and just do my expression here? So I need two things. I need my input, my R of S. I need to know what the input is, because the input could be a step, ramp, or parabolic, right? Because we talked about it could be those three cases. So, and we actually could put one more in there if we wanted to. It's called jerk. So if you want to see how fast something accelerates, that used to be a very common thing. I don't know, there was a student here 15 years ago who was really into high-end RC cars, and how fast something could accelerate, I guess, was a performance measure. That was called jerk. So I added in some stuff about that just for him, but I don't think people talk too much about that anymore. So I need the input, and I need the open loop transfer function. Okay. So my open loop transfer function, and I think I either have talked about this, I have talked about it, or I will talk about it at the end of this chapter, I can't remember, is just equal to G times H. Okay. So once I have that, I can solve for my steady state error. I've been talking away. So now let's look at how we can focus, because if you remember in our expression here, the only thing that really is going to have, so from the system, the only thing that has S terms is right here, this GCGP term. So let's write that generically. It has a numerator and it has a denominator. And I'm really only interested in the denominator, because remember, that's our characteristic equation. And that's what's important to us. So we factored this out so that we have all these coefficients here. We have an a to the 0, and then we have an s multiplier over here. This s to the n is equal to the number of 0, or poles, I should say. So that's equal to the number of poles at s equals 0. It's also another really important thing. Let's look at n is equal to 1. So let's say n is equal to 1. So our numerator function is here. Our denominator function is here with all those a's. And then this is s to the 1. Let's rewrite that as a numerator of s. And here's our denominator. But let's pull out over here 1 over s. What is 1 over s equivalent to in the time domain? Multiplication by 1 over s. Multiplication by 1 over s, that's a property, but that would be an input. Multiplication by 1 over s is a property, a mathematical property. No, you're close. Begins with an I. Integral. Yeah. 1 over s is an integral, isn't it? And we already talked about, if something has the ability to integrate, it can remember, so it can take the system 0. So not only is s the number of poles, but it's also n is equal to the number of system integrators. And that's so important to us. We say that the system type is equal to n. So if it's a type 1 system, that means it's got one integrator. If it's a type 2 system, it has two integrators. If it's a type 3 system, it has three integrators. Now, does anybody have a hard time with me saying that a system has integrators? No real world system has an integrator, right? It's just a decaying exponential or sinusoidal waveform. Where do you get the integrators from? I gave you a hint earlier. What did we add into our block diagram? We had two blocks. One was the plant. What was the other one? The controller. So I can add more integrals or more integration by just modifying my controller. So if I'm trying to keep up with a step, I only need one integrator. If I want to keep up with a ramp, I need two integrators. If I want to keep up with a parabolic, I need three integrators. Okay. So you get the integrators from the controller, not from the system. Okay. So that is a pure integrator. N is our pure integrator term. Okay, so now let's go ahead and do some cases, because what we're going to do is we're going to see if we can simplify that ESS equation a little bit, if we can at all. So let's take the first case where we have an input of a unit step. Okay, so as Moses said earlier, it's 1 over S. If it has some random value of multiply, it's a 12-volt system or 12-volt DC input, it becomes A over S. So we're going to plug in our unit step input and convert that to the Laplace domain so that R of S becomes A over S. Now we're going to take the limit function. So our final value theorem is S F of S. So here is our S. Our F of S is A over S times 1 plus GC GP. Okay. Well, what do you know? Those two will cancel. Right? What about this over here? No S terms in it, right? So I can move this limit over to here because 1, I can change S all day and night, and it's still going to say 1, isn't it? It doesn't go away. It's always going to be 1. So I move my limit function over to my GC and GP, and now I'm going to come up with a new term. This term here, this KP here, is called my proportionality, a proportional constant. And I'm not sure what's going on over here. That kind of stepped out. But K sub P is equal to the limit as S approaches 0, GC, GP. Okay. So that's going to be a number. And then my ESS, once I have K sub P, I plug that into here, and that's going to be my steady state error. So to solve for your steady state error in this case, we only have to solve for K sub P. So K sub P is equal to the limit as S approaches 0, GC GP. Once I have that value, I plug it in for A, plug it into A over 1 plus KP. Remember that value of A is the magnitude that I have there, and that gives me my steady state error. Now, understanding a little bit about, remember I talked about proportional only constants? If I had a proportional only controller, how do you minimize the amount of error in your system? Based on this. I would like the error to be as close to 0 as possible. What do I have to do to K to make it have as small error as possible? K is in the denominator, right? What's the smallest error you could get? No error, correct? So how do I make ESS equal to 0 in this case? What does K need to be to get ESS equal to 0? Yeah, make it go to infinity, right? So how do you get systems to be in the real world to have no error? You have really big values of K, really big gain constants, huge, 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 10 million. The problem with that, though, is that you're going to have big jumps in your process, right? Anytime you have error, your system, your controller is going to respond really with some high value, which could make your system unstable, the actual physical system unstable. But that's what you do to make your system go to 0 error. If you don't have an integral constant in there or integration in there, you just go ahead and jack up your proportionality constant. So that's K sub P. That's proportional or position. I should have called it position, so I apologize. Position error constant. So if it's a type 0 system, no integrators, that means we have to get error, right? If S is equal to, excuse me, if S is equal to 0, then what we have is S to the 0 times whatever is in our coefficients. This is equal to 1, so this is S. I don't know, let's say S cubed plus 2S squared plus 3S plus 7. When S approaches 0, I'm still stuck with 7 here, right? So for a type 0 system, I don't cancel out any of those coefficients. If this was a type 1 system, and I had this value, at the limit then, as S approaches 0, goes to 0. So my K sub P term becomes an infinite, right? Because we have, well, in the denominator, we have this, which is 1 over. So that becomes infinity. Let me show that again. This is equal to my G sub F, my GC. GP has a numerator and an S to the N times a coefficient, right? So if I take the limit as S approaches 0, and if this is equal to 0, here's my numerator, here's my denominator. What I'm going to end up with is whatever coefficient is there, right? Because this one is equal to 1. So all these terms that are in the denominator, like I said, this is S cubed plus 2S squared plus S plus 7. Then these terms all go to 0, but I have a 7. So my K sub P becomes whatever my numerator is divided by 7. So that's not going to be a 0 number. But if I have S to the 1 times my denominator, that equals 0. Anything divided by 0 is infinite. This becomes infinity, and my steady state error goes to 0. So by adding an integrator, my my position error constant goes to infinity, which means my steady state error goes to 0. Okay. So for type 1 system, I get no error. One integrator for a unit step input is all I need to make that error go to 0. What about greater than type 1 system? Type 2 system, 2 integrators. Well, if it's 2 integrators, when I do my limit as S approaches 0, my numerator over S squared times my denominator, what happens as S approaches 0 here? Does anything change because it's S squared? It's still 0, isn't it? So for a type 2 system, you're also going to have no error. Type 3 system, type 4, type 5, and on and on and on. So if you're only going to provide a unit step input, you only need a system type 1 integrator. You don't need a type 2 or type 3 because those cost money, right? That's additional programming or whatever you need to do to make that work. So we can start to generate a table, right? So let's see if we can bring up a table. Let's start generating a table. in whiteboard. So this will be input. And then let's see, we'll say K sub P and ESS, which we said is going to be equal to, well, let's put it actually in the table. It's easier this way. So K sub P here is going to be equal to the limit as S approaches 0. GC times GP. My input for a step is going to be equal to, and let me see, do I want to put, and I got to do a type system too, right? How do I want to do that? Am I trying to put too many dimensions here? I think my system type has to go over here. Let's put this on top. See if this works. Okay, so for a type 0 system for a step input, my K sub P is going to be equal to my limit as S approaches 0, GC, GP. My steady state error is going to be equal to some value, whatever my unit step input is, 1 plus K sub P. Let's go to a type 1 system. So this is ESS. This will be K sub P. What's going to happen with K sub P? Well, we already said for a type 1 system, K sub P is going to be equal to infinity, right? Because 1 over S as S approaches 0 is going to be equal to infinity. So ESS is going to be equal to 0. For a type 2 system, so this is infinity, 0, and on and on and on. So we can start to create a table just based on knowing the system type and knowing the input and what we need to calculate. All right, so let's go back here and now go to our ramp input. And a ramp input in the time domain is A times T. We include the unit step just because we wanted to start at T greater than 0, so we can do a unilateral, right, Laplace. Otherwise, if we have it going in minus time, it gets to be a real pain in the keister. So our ramp input, AT times my unit step, that in the Laplace domain is A A over S squared. Okay, so now let's plug that into our base equation, which is the limit as S approaches 0, S times my input, R of S, over 1 plus GC times GP. If I put my A over S squared in here and I distribute it, well, the first thing I do is I see that that term goes away and that term becomes just an S, right? That S is multiplying the denominator, so I can move that here and multiply those terms. So that becomes S plus S times GC GP. Now I'm going to move my limit over here because that's the only term that has any S functions. So I'm going to move it here. What happens to the limit, or what happens when I say limit as S approaches 0, S? What's that equal? Zero. I'll give you a hint. The easiest way to do this, for me for doing limits, is actually plug in the number. Plug in 0 and see what happens. If you get goofy numbers like infinity, then okay, then you got to start looking at it as the number gets really, really small. But for most cases, if you just plug in the number, it usually works its way out. So you don't have to think about it all that hard. So 0. So this term goes away. So all I'm left with is A over the limit S times GC GP. Well, let's take a look at this. SGC GP. Have we ever seen a GC GP term? If we look over here, our case of P term looks pretty close to it. It's GC GP. When I multiply S times K sub P, or my position error, and I multiply it by S, what would be another way to say that? Multiply K sub P times S. Multiply the position times S. What is multiplication by S in the Laplace domain equivalent to? Taking the derivative. If I take the derivative of position, what do I get at? What do I get? Velocity. So the case of V. And K sub V is my velocity constant or velocity error constant. Because I'm taking S, I'm taking my position constant, taking the derivative of it by multiplying by S to get my velocity constant. So I'm going to have K sub V. And here's my value, my expression. S GC GP, it's my velocity error. Now, let's go back to our systems. So let's take a look at our, let me copy, let's do this here in whiteboard. Oh, right here. Oh, it's not awake. Why isn't this moving? Oh, sorry, folks. It looks like whiteboard is crashed. No. All right, so we said K sub V is equal to the limit as S approaches 0, S GC GP, right? And we already said that GC GP has a numerator over some S to the N times my, well, let's write it out as an expression. A0 S to the N minus 1, etc., all the way down to A to the N, but no S terms. So let's start off with a type 0 system. So a type 0 system, my GC GP is going to be equal to S to the 0 over A0 S to the N minus 1 all the way down to AN. That's equal to my numerator over and this becomes a 1, right? S to the 0 is just a 1 term. All right, so what do we get when we have a type 0 system? We would have a number over A sub N, right? But remember, this is multiplying by S, correct? So for a type 0 system, that's our value, but a type 0 system where we have S multiplying by our numerator over S times A0 S to the N minus 1 plus all the way to the N. That's going to be equal to S times my numerator over A to the N, correct? Don't forget, I now have to take the limit as S approaches 0. So for a type 0 system, my velocity constant is going to be equal to 0. So a type 0 system, no integrators, my velocity constant is 0. Now I'm going to go back and plug that into this equation here, a over 0 equals infinity, right? So let's think about that for a second. If I was to draw that graphically, here's my plot. So if I have an input over here, if I have a type 0 system, so this would be type 0, I have something like this, right? And then over time, here's my error is E steady state. This is the difference between the two. For a type 1 system, for a type 0 system. If it's a type 1 system, I end up doing something like this, and I might overshoot, but eventually it'll balance out, it'll be the same value. Okay, so there'll be no steady state error. Now let's look at for the case for a ramp. A ramp is doing this, right? So for a type 0 system, that's not like that, right? Its characteristic doesn't change. So now with a type 0 system, as this continues to increase, this stays constant. So the error between those two just continues to grow and grow and grow. So that's why the steady state error is infinite, because at time t approaches infinity, that ramp approaches infinity, but the type 0 system, it just stables out to a value. But a type 1 system, it's doing this, and then this one is ringing, and it can continue, but it basically will have a constant error between the two. So for a type 1 system, we have s to the 1 in our GC/GP term. Those s terms will cancel. Remember that s that we had? We just had it in the numerator. As s approached 0, it forced the whole thing to 0. Now that get canceled out. And so now what we're left with is we have that a over the a to the n term. That is not a 0 number. So my steady state error is non-zero. Okay. If I go to a type 2 system, now this cancels out. This becomes a 1 as my limit function approaches 0. Anything divided by s as it approaches 0 becomes infinity. So my case of b term approaches infinity. My steady state error approaches 0. So for a unit ramp input, I need a type 2 system to get to 0. So let's see if we can go back and append to this table. Now for a ramp input, I'm not even going to care about case of P. I'm only interested in the case of B, because case of P is the position constant. That's the one that I define for a step input. For a ramp, I'm interested in case of B. So my case of B is equal to the limit as s approaches 0, s, GC, GP. And we've already said that that's going to be equal to 0. My ESS is equal to A over case of B, which is equal to infinity. So for a type 1 system, a type 0 system, sorry, I'm definitely going to get a value that doesn't work out for me. For a type 1 system, my case of B term is going to be equal to the limit as s approaches 0, s, GC, GP. But remember, the GC, GP has one s in the denominator, so that cancels out. So that's going to be an actual number. Okay, that's going to be equal to GC times GP. All those terms will cancel out. I have no integrators. I think actually I probably should include that in here just because we'll forget to clear that out. So that is not a 0 now. 0. That is an actual value that you have to calculate. So then my ESS is equal to E over K sub B. For a type 2 system, my K sub B is equal to infinity. And my ESS, oops, I already have that up above, is equal to 0. If I go to a type 3 system, here's my K, here's my ESS. So now instead of writing a K sub P, remember, I'm only interested in the K for the input. So the input is position for a step or velocity for a ramp. So instead of calling these KPs, let's make this generic. And let's just call this K here, just to keep it more generic. So for this system now, this is always going to be the case, 0 and infinity. My K sub B term, so this is K sub P. My K sub B term is equal, whoops, I called that 0. It's the other way around. Sorry about that, folks. This is infinity, 0, infinity, and 0. So as long as I exceed the system type where I actually calculate a value of K sub B, so you can see this K sub B here is a non-zero or non-infinity number, I can actually get a non-infinity or non-zero ESS. Anything to the right of that is going to always have a steady state value of 0. Okay, so the last one, which is parabolic. So the parabolic is something that is increasing exponentially. So a step input was a constant. A ramp input is the integral. So let's go a step is a constant A. A ramp is the integral of a step, which is AT, and a parabolic is the integral of a ramp, which is AT squared. If you think about that, you can draw that here. Here's a step input, right? It's constant. Let's integrate that. Now I have that. Let's integrate that. And I have something that does that. So I'm just integrating those through to get those terms. So for a parabolic input, I'm integrating it. That's why you can see here too, it has S cubed, right? So I take a step input, which is 1 over S. I integrate it, which is multiplied by 1 over S. I get S squared. And if I integrate that one more time, multiply by 1 over S, I get a number over S cubed. I get a parabolic input. So plug in my input here to that original expression, S times R of S over 1 plus GC GP. Cancel some terms out. That becomes an S squared. Now this becomes S squared multiplied through here. And if I move my limit function, what is the limit as S approaches 0 of S squared? Remember, don't overthink it. Just plug in your value, your limit value. What do you get? Make it even easy. Just call it 0. 0 times 0 is 0. You could get fancy and apply that. This is not a true math class. So this is 0. So that term goes away. This term, I need to evaluate further because, oh, wait a minute, this is backwards. hold on, sorry about that, folks. I have a typo here. Yeah, this over here, I inserted it in the wrong spot. And let's see if I can do that. Oh, let me just delete it this way. There's the insert button. There you are. Okay, doesn't super line up. Let's see if I can do it this way. Not perfectly lining up. I don't know why. Cheat this over a little more and see if I can get there. Sometimes Microsoft auto scales things. See if I can make this a little bigger. Will that give me? Okay, so I just needed to scale it up. There, okay. Sorry about the typo. But you can see how the s squared cancels for the first term because of the limit function. So now all I'm left with is s squared GC GP. What is the derivative of the second derivative, right? Because taking and multiplying something in the Laplace domain by s squared is the same thing as taking the second derivative. What's the second derivative of GC GP? Another way to say GC GP is the position constant. What's the second derivative of the position constant? Acceleration. First derivative was velocity. We got k sub b when we did the ramp input. Second derivative of position is acceleration. So we will call that k sub a. Okay. So if we go back to our table, so now we know k sub a is a over s squared GC GP. So let's go back over here. So now we have our Ka term, which is again, we're only interested in it if our input is a parabolic. For the other terms, we don't care about it because we don't have to keep up with it. It's not something that's continuing to accelerate, right? So if you think about it, the position, it doesn't accelerate, it stays constant. So we're only interested in position. In a ramp, it's continuing to increase its position, so it's got velocity. So we're interested in the velocity constant. In acceleration or in a parabolic, it's in continuing to increase its position, not just the position, but the rate of the position change. So that's the acceleration. So we're interested in Ka. So Ka is equal to the limit as s approaches 0, s squared GC GP. So let's do the type 0 system. Let's do the limit as s approaches 0, s squared, some numerator over s to the 0 times my denominator. Well, this is just a 1. This term is always going to be equal to 0. Limit as s approaches 0, s squared is always going to be 0. So that makes that term go to 0. So for a type 0 system, this k sub a is going to be equal to 0. My steady state error, which is equal to a over k sub a, is equal to infinity. So for a type 0 system, we have infinite error because we have no integrators to help us. Let's take a look for a type 1 system. Limit as s approaches 0, s to the 1, s squared, sorry, s to the 1 times my denominator. Same deal. This cancels. That becomes a 1. That's still 0 there. So this is equal to 0. and my steady state error is still infinity. Let's go to a type 2 system. Limit as S. Why isn't this writing? S squared, numerator. Now I'm going to spell out my denominator because I've got the S squared there. So this is A n minus 1, S to the n minus 1, plus dot, 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 all the way to the A to the n. That's going to be equal to, now these two terms will cancel, will become the numerator over my A sub n term. That is not a 0, nor is it infinity. So for a type 2 system, my Ka is equal to the limit as S approaches 0, S squared. I'm gonna have to zoom in a little bit, sorry, and then I'll zoom back out because I can't write that small. So my Ka is equal to the limit as S approaches 0, S GC, S squared, GC, GP, which is not going to be a 0 number, okay? That's going to be a valid number. And then my ESS is going to be equal to A divided by, I don't know why this is falling behind, K sub A. So for a type 2 system, for my parabolic input, I'm going to go ahead and get a non-zero value or a non-infinite value. Let's go to the last type, type 3. The type 3 system is the limit as S approaches 0, S cubed, S squared, keep putting this in the wrong spot, numerator over S cubed times my denominator. That cancels and that becomes a 1. So this is going to equal any number over 0 is infinite. So ESS here, or Ka, is equal to infinity, and ESS is in fact equal to 0. Okay, so I'll try to highlight this as best as I can, but you kind of follow the diagonal here. See if I can follow the diagonal. So that's kind of the dividing line. That center line, if that is the system type based on the input, you get values. Anything to the right of that, you get no errors, right? Steady state error 0. Anything to the left of that, you get infinite. And that's how that table divides. So let's go back to this. So K sub A is our acceleration constant. Type 1, type 2, type 3, or greater, you have that value. All right, we'll finish up with this because I'm drying out rapidly. My lips are on fire. So we're doing it with the closed loop system. So this is a closed loop system that we're analyzing because the error is closed, but we're actually looking at the system type for the open loop. It's just GC, or the feed port gain, and the feedback gain. So G closed loop is G over 1 plus GH. G open loop is just equal to GH. So essentially, that is my open loop gain. All right. If you get confused, I always do my summing junction here. And I just do 1G here, 1H, and then I open loop this. So this is my my R, and let's call this my C. So what would be the open loop gain? I can see to get to point C, that's equal to R times GH. So my transfer function for C over R is equal to GH, right? So that's the reason why we call it open loop gain. If you take a look over here, we literally, oh, We literally disconnected that loop. That's why it's open. We pulled the terminal going into the negative. We pulled that open and we're just looking for the comparison between those two. So that's the primary difference between closed loop gain and open loop gain. Open loop gain or closed loop gain is interested in the output over here. Open loop gain is interested in the difference between the two. Okay. So let me hide this real quick. So that's our open loop. Again, if we needed to, if we don't want to use unity feedback, but oftentimes we try to because it's hard to calculate error if you don't know what you're comparing your output to, but it works out okay. It's just sometimes some books have unity feedback, some books have H, so I've seen it either way. We'll just do it with unity feedback just to be consistent with the book that I'm suggesting that we, or recommending that we use. And then your error is going to exist if your desired value, your set point, is different. So how do you fix that? You just add a controller, add a proportional integral. Now, most applications in the real world, your set point is going to be fixed value. Your tank level is 60%. It's only when you start getting into really elegant controls and maybe more robotics. Like I said, when you're trying to get the position away from a certain location, that would be a ramp. But I think for most of us in EET, we probably will just look at a fixed set point. The reason why I teach the stuff with the different system types for the different inputs, because if you look at the FE review manual, it has a table for type 0, type 1, type 2. It has all those and those proportional constants. So it doesn't take a lot of additional work to go ahead and explain the error of the system type stuff. And let's just look real quick to see. Let's see if we can actually, I don't want to review course. I just want to see the. Oh, we might have to have a. I don't think I have a login, but I was just looking for the electrical one. I don't want to download anything illegally. But if you take a look at, if you set up an account, because that would be smart for you, because I think all of you are required to take the FE, is to go to the exam review material. Let's see, what does this say? Reference handbook. Yeah, you got to buy it, but you can download it for free. So, oh well, would you feel comfortable sharing your screen? That's what I'm saying. Share your screen in Zoom. Oh, you're not in Zoom. Oh yeah, if you want to email it to me, yeah, that'd be great. I just don't want to download anything and get anybody in trouble. But if you look at the controls section, I believe, I'm not 100% sure, but I believe that the way that they do that is they actually have, that table in there and they show you how to calculate it. Or, well, yeah, you don't have Zoom set up. If you had Zoom set up, you could set it up on the chat. If you don't have it quickly, that's okay, Moses. It's not a big deal.
I have the FE handbook, Paul.
Oh, Mort, do you want to share your
PDF download? I can just send it to you in the chat if that works.
Yeah, you want to take a picture and send it to us in the chat?
Yeah, let me try to get to the table.
Okay.
It is a few years old, so I don't know if it's.
What's that?
Mine is a few years old, but I'll see if it's.
Yeah, Moses, it's still not here, so it might take a few minutes to get it processed. Did you share it, Mort, or in the chat? I don't see it yet.
Yeah, just a second.
Okay, sorry. Nope, Moses is here, so let's try that one. So let's go to
You got me beat.
Thanks, Mort. Sorry for let's look in the controls section. So electrical and computer engineering. Voltage regulation. Where's the controls stuff? They used to have just a one, it was like 80 pages or something like that, where. What page is that? 225. Okay. There you go. So that's the reason why I cover those other systems, because again, in EET, we probably won't do it, but you can see unit step, they call it case of B. The case of B doesn't appear that they even show you how to calculate that. So unless it's up above here. Yeah, they don't even show you. They just give you case of B. So case of B for that. So that they're missing a little bit of information, but you can see system type 0, 1, 2. If you go on and on, you just put zeros here. But unit step, ramp, or parabolic, this is not case of B. That's the limit as S approaches 0, S squared GC GP. This is the limit as S approaches 0, S times GC GP. In this case of B, so this is a different value. So they're missing some information, but that's the reason why we just put the other systems in there, because if you can do this really quickly, this is 4 or 5 points, pretty easy on the FE. It's a pretty simple question. So, okay. Well, thanks for sharing that, Moses, and thanks for trying to share that, Mort. Any questions? Yep. Yeah, so if you know your system type, well, let me back up. If you know what your input is going to be, if you're trying to control to a fixed input, then you want one integrator. If you want to control to a ramp input, you need a system type 2 to have a chance. Right. Yeah, it's very rare that a system has an integrator built into it. That'd be pretty unheard of. Most of them are first order processes, second order process that has exponential decay. It's highly unlikely that you'll find one that way. So I would just say, all right, well, I need a controller that's going to be able to handle a ramp input. Then I know I need, if I'm willing to tolerate some error, that's just the ammonia tank. I think it's ammonia or hydrogen blowing, letting out some pressure. That happens every once in a while. But you would use that here. If you want it to be 0, then you need a type 2. Okay, any questions? All right, well, no questions. Have a great day, everyone. See you on Thursday. Take care. Yep.